This is Advanced Math, Unit 8, Lesson 5. You should have this sheet of notes in front of you. If you are watching this online, this should be posted as well so that you can print it out and fill it in as we go. Okay, for each of the following sketches, is the graph a function? Yes or no? If so, state the domain, the range, and where the function is increasing, decreasing, and constant. All of these will be on the test. Remember, only the range is described in terms of the y values. That's important to know. The range is the only place where you use your y-axis. Everything else we use our x-axis to describe the domain, the increase, the decrease, the constant. Range is the only place we look at the y-axis or y values. Okay, function. You should remember from previous math classes, you test if a graph is a function by doing the vertical line test. The vertical line test, you remember doing that last year to test if something is a function. If it touches the graph more than once, it is not. Would you guys agree that all the way through this graph, it only touches the graph at one time with each vertical line? So we would say yes, it is a function. Something like a sideways parabola, like that would not be a function because it would not pass the vertical line test. Okay, domain. Domain, we talked about in notes on a previous lesson, is the set of all x values. Domain is the set of all x values. So I look left to right, and when I look off to the left, even though the graph is opening up, is it going upward towards the left forever? Yes, it is. This side's opening upward, but is it going towards the right forever? Yes, this arrow is going to go off to the right. This arrow is going up, but towards the left, so we would say negative infinity to infinity. Your range is a set of all y values, and you can see that this graph does not go up and down forever. And when you read your range, you go from the bottom up. From down here, there's no graph, no graph, no graph. But at -1 is where the graph starts. And you see there's no open circle there. It's all closed in. So it's a bracket, -1. And then it goes up forever. This one may be going up and slanted. This is going up and straight. But it's still going upward in the upward direction forever. So we would say -1 to infinity for the range. -1 to infinity. Okay. Increasing, decreasing, constant. Remember what was said earlier about using the x-axis for everything except for the range? This is the only time you use the y. Domain, increase, decrease, constant. You're always reading the x-axis. You do have to remember that because kids stumble up on that on the test every year. Okay, increase. You read your graph from left to right. For example, from here, kids will say, oh, well, that's increasing, but I'm going the wrong way. Going from left to right, if you're going from left to right, that is a walk downhill. This is constant. And then this is a walk uphill. So this piece here is the increasing piece. And remember, we read the x-axis. At what x value does it start to increase? That's an x value of 2. Now, you do not have to draw that in there. I'm just trying to show you. Again, I'm going to erase this in just a little bit, that to the right of that dotted line, I am increasing. To the left of that dotted line, I am decreasing, and everything in between, I am constant. So what are my x values? That's an x value of 2, and this graph doesn't come back down. It stays increasing from forever on after 2, so we'd say 2 to infinity. And there's no open circle there, so we put a bracket. When is it decreasing? We said it was decreasing on this left side. Now, the left side is coming from -infinity, and then it stops decreasing at what x value? That is 1. And again, there's no open circle there, so I put a bracket. Okay, Now, kids will often tell me, Mrs. Torres, this is going upward. If I'm going upward, why do I have negative infinity? The reason is the kids who are saying it's going upward, yes, it is, but when you're looking upward, positive infinity, you're reading the y-axis. And you're supposed to be reading the x-axis. Leftward, it's coming from the left, which is negative infinity, and then it stops decreasing at a x value of 1. Okay, so it's decreasing all of this over here all the way up to 1, and then it's constant, and then it increases from 2 on. Okay, constant is between -1 and +2. You want to be careful with that. And sorry, I should have put a -1 there. I hope I said it when I was talking. -1. Okay, so it's decreasing from negative infinity to -1. All right, and then it's constant from -1 to +2. The one part you want to be careful with here on those numbers, and here's why. You already put a closed circle on the -1 and the +2. If you put brackets here, then you would put another closed circle on closed circles that are already there, and then it's not a function. So you put parentheses. What I tell my students, and it's totally up to you, so that they don't get confused, I just tell them when you're doing increase, decrease, constant, just use parentheses everywhere so you don't get confused. Technically, that's not the truly mathematical way of doing it, which I'm okay if you do it the right way. If you do it that way, and you mess up and you put brackets in place where they shouldn't be, I will mark it wrong, so keep that in mind. If you're nervous and you just want to use parentheses on all increase, decrease, constant, go for it. I will not mark it against you. If you think you can handle it and you can put your brackets where they belong or your parentheses where they belong, and keep in mind, I could put the brackets here if I choose to, and the parentheses there. If you don't like any of that and it's confusing, just use parentheses. All right, next one, function. Vertical line test again, and you can see all the vertical lines will always pass the vertical line test. There's no place where it crosses it twice, so we're going to say yes. Domain is the set of all x values from left to right, leftward and rightward, negative infinity to infinity. If you remember, that's always true for parabolas. Parabolas always have a domain of all reals unless there's a restriction. Yes, it's going downward, but it's getting off to infinity. It's getting really, really wide in the leftward and the rightward direction. So it's negative infinity to infinity. Okay, range. The graph does not go up and down forever. Remember I said you start reading it from the bottom. There's a graph because these arrows are going downward forever. So there's a graph all from down negative infinity, and it keeps going and going and going, and then it stops at what y value? It stops at 3. So you would say negative infinity to +3. Now that one you do have to put brackets because if there's no open, if that was an open circle, then I would put parentheses. But since there is no open circle there, I'm putting a bracket and always parentheses for the infinities. And I said earlier I would erase those. If you leave them there, that is okay. Okay, so domain, negative infinity to infinity. Range, negative infinity to 3. Again, that should be reviewed from last year. Increase, decrease, constant. First, recognize that there is no constant. I'm going to put my dotted line here. On the left side of the graph, I'm increasing. On the right side of my graph, I am decreasing, and there is no place where it's constant. I'm just going to put an X there. Okay, again, reading your graph from left to right, on the left side is a walk uphill, that's increase. On the right side is a walk downhill, that is a decrease. Okay, so when is it reading the x-axis for all of these? There is no constant, but we still read the x-axis. When you're increasing, you're coming from negative infinity to what x value? 1. And I'm just going to use parentheses so I don't have to worry about it later. Okay, negative infinity up to this value of 1. You can see that I am increasing. This is all a walk uphill forever and ever and ever until I get there. till I get to the 1, and then I'm no longer increasing, I start to decrease. So when do I start to decrease? From that x value of 1, and then I decrease off to positive infinity. Remembering what I said, kids will say, but Mrs. Torres, you're going downward. If you're going downward, why did you put positive infinity? Because my positive infinity is coming from reading the x-axis, and I'm decreasing going off to positive infinity. If you're reading it as negative infinity, you're reading the y-axis, which is not what I'm supposed to be reading for increase, decrease, or constant. The range is the only time I look upward and downward. Okay, so increasing on the left half, that's negative infinity to 1. Decreasing on the right half, that's 1 to infinity. All right, number 3. Passes the vertical line test. Any vertical line you draw, it's going to pass. So is it a function? Yes. Domain is not negative infinity to infinity like it was for the numbers 1 and 2. At what x value does it start? It starts at negative 2. I almost put infinity. It starts at negative 2 with a bracket because there's no open circle there. If there were, I'd put parentheses, comma, and when I go off to the right, it is going off, because of that arrow, it's going off forever. So it's going off to infinity. The domain is negative 2 to infinity. And the range, I come from the bottom, there's no graph, and then the graph starts, boom, at negative 1, and it goes up forever, off to infinity. And I put a bracket again, there's no open circle. Does that make sense? So there's no graph down here. It starts at the negative y value of negative 1, and then it goes upward direction forever, so off to infinity. This is the only place you read the y-axis. Okay, now I'm hoping you recognize my graph is only increasing forever and ever and ever and ever. It's never constant. It's never decreasing, so I'm just going to cross those out. It's only increasing forever and ever and ever. At what x value do you start increasing from? Negative 2. And how long does it increase? Forever after that, so off to infinity. If you put brackets there, that's okay. I said that earlier, you could. Up here, you would only put brackets either there or there if you're choosing to use the brackets. You cannot put brackets on both, there or there. And on this one, since there's only the negative 2 once, because there's no decrease in constant, if you put a bracket, that's okay. Again, if you don't like it, just use parentheses and be safe. Okay, number 4. Does it pass the vertical line test? It's a little tricky. Right in here, does it pass the vertical line test? Now, it looks like it doesn't, but because that circle is open and that circle is closed, it does pass the vertical line test. Does everybody see that? You draw it, it's open, it's closed, so it's really technically only passing that one dot right there. Okay, so yes, it is a function. Domain, does the graph go left forever? Yes. Does the graph go rightward forever? Yes. Is there ever a place in between where there is no function on the x-axis? Like, for example, is there ever a time where I go over and up or down and there's no graph? There's always a graph. No matter how far over I go, there's going to be a graph. No matter how far over I go this way, there's going to be a graph. And even right here, 1, 2, negative 3, at this one spot, there's no graph there, but there is a graph there. So there's always a graph. So we'd say negative infinity to infinity. And these, by the way, are the piecewise graphs that you did last year. All right, so negative infinity to infinity, because there's nowhere here where I do not have a graph. That's the only point that's a bit concerning. There is no graph, but there is a graph there, so there's still a function at negative 3, a graph. Okay, range coming down. This arrow is going downward forever, so it's coming from negative infinity. And then it comes up and it stops at a y value of 1. Now that 1 has a close, I'm going to put a bracket. So negative infinity to 1, union, there is no graph in between 1 and 2. That's why I'm using my union, because there's no piece there. So I cannot use like 1.5 or 1.8. But then it picks back up at 2. And it stays constant at 2. Do you see that it's constant? It doesn't go up, it's just constantly 2 forever and ever after that. Now it's open at this spot here, but it is closed at other spots. This is my y value of 2. So is there a graph at a y value of 2? Yes. It may be open at this one piece, but it's closed in at other pieces. So we would put union 2. The y value of 2 is a part of the graph. Okay, increase. Can you see that there's no increase anywhere? Decreasing is from here on, so what is that x value? -3, let's just use parentheses, comma, and it's going downward. It's decreasing onward, going towards the right. Going towards the right is positive infinity. Okay, so it is decreasing for how long? Forever, going towards the right, and going towards the right is positive infinity. Constant is over on this end, and it's going constant forever to the left, so that's negative infinity. And it stops being constant at the -3. If you are using brackets, you cannot use brackets there. It would have to be there. You don't have a choice on this one because this one there is an open circle. If you're not using brackets, don't worry about it. Okay, let's flip on over to the back side. All right. Classify a function as even, odd, or neither. A function is even if for every x in the domain of f, f of -x equals the original function f of x. We call that even. A function is odd if for every x in the domain, f of -x does not equal the original but equals opposite of the original. So you have a function, you plug in -x to all your x's, change all your x's to -x. If it equals the original function, we call it even. If it equals the opposite of the original, we call it odd. Now, a really quick side note, I don't know if you remember these even-odd functions that we did first semester. It was with sine, cosine, tangent. I'm going to use f of x equals cosine x. F of x equals cosine x. And I'm going to apply this rule. What happens when I use f of -x? That's cosine of -x. Now, do you guys remember from last semester what the cosine did with the negative? Did it absorb it or kick it to the front? It absorbed it. So f of -x equals cosine of positive x. Do you guys remember that? Cosine absorbed the negative, so it's just cosine of x. So f of -x equals the original function. Do you see cosine is the original function? So we'd call that even. That's why we called them even odd. I don't know if you recognize that we called them even odd, but we did. The odd function, there were two of them. I'm only going to do the sign. I will call f of x sine of x. You can call it tangent of x was the other one. We'll change this to g just to use a different letter. G of x equals sine of x, and let's apply this rule. G of -x equals sine of -x. And what did the sine function do with the negative? Did it absorb or kick it to the front? It kicked it to the front. So you can see g of -x, did it equal the original function or the opposite of the original function? Here's the original. Here's what it equals now. So it's not the original, it's the opposite. It's the opposite of the original, so we call that odd. All right, so let's see if we can apply that here. I'm going to find f of -x. I put blank where my x's should be. And in those x's, I'm going to plug in -x because I'm finding f of -x. -x times -x is positive x squared minus 5. F of -x equaled, is it the original or the opposite of the original? Right here, it is the original. Do you see that it is the original function? If you plug in a negative for your x and you end up with the original function, you would call that even. All right, let's try this one. G of negative x, because that's what we do. We plug negative x into all the x's. 7 over blank squared minus blank. And in the blanks where the x's used to be, I'm going to plug in negative x, and negative x. Negative x times negative x is positive x squared, and minus a negative is plus x. Okay, this kind of looks weird. I'm going to put that on the side so you know that's not part of this problem. It kind of looks, and I apologize. That right there should be a cubed, which is going to change this. Okay, negative x times negative x times negative x is negative x cubed. Okay, so one more time, negative x, that minus the negative became plus, negative times a negative remains negative, negative x cubed. All right, now it's hard to tell, like, is it the same, is it not the same, is it the opposite? What I would suggest, the 7 is 7, just leave it. Pull a negative out of the bottom, because then it's easier to tell. So I'm going to pull the negative out. I'm just going to put it right there. Parentheses. That becomes positive x cubed, and that's minus x. How did I get that? I pulled out a negative sign. Pulling out the negative, I just put it to the top of the middle of the fraction. The negative x cubed became positive. The plus x became minus. So this is what g of negative x equals. So looking here and looking at the original, is it the same as the original or the opposite of the original? Here's this, with the opposite side in front. It is the opposite. We'd call this odd. Why is it odd? Because everything is the same except for the opposite sign there, the negative sign. That means it's the opposite of the original function. All right, u of negative t, square root of 3 minus blank squared, and that time it is blank. And in the blank, I'm going to plug in a negative t, and that gives me u of negative t equals a square root of 3. Those two negatives do not cross out. I have to do order of operation, which means I do my exponents first. And negative t times negative t is positive t squared. So u of negative t gives me 3 minus t squared. Is it the same as the original or the opposite of the original? 3 minus t squared. There's no opposite sign out here, so it is the same. We'd call that even. All right, next one, h of negative s equals blank squared minus 3 blank plus 1. I like putting blanks in and then just plugging the negatives in. And we're plugging negative s in where all the s's were originally. Okay, negative s times negative s is positive s squared. Minus 3 times negative s is plus 3s, and then plus 1 stays plus 1. Now, if it's not easy to tell, for example, this one was easy to tell that it was the same as the original. This one was easy to tell that it was the same as the original. When it's not easy to tell, then factor out the negative to see if it's the opposite. Okay, here's the original, and here's what I have. I can tell it's not the same, so I'm going to factor out a negative and see what happens. Negative s squared, because I'm taking out a negative, minus 3s minus 1. Okay, so the opposite of this, is this the original function? Positive, negative, 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 positive, negative. It is not the same. So it's not the same as the original. It's not the opposite of the original. So we would say neither. All right, so here is what we got before we took out the negative, and you can see that it's not exactly the same. So we factored out the negative to see if it's the opposite, and it's still not the opposite of this because you can see the signs are off. So if it's going to be opposite, it has to be the opposite of everything. Opposite of that would have to be plus, and that would have to be minus. That didn't happen, so you'd say neither. Okay. How do you tell with graphs whether it is even, odd, or neither? If you had a graph like this, I'm going to do number 10 first. If it is symmetrical about the y-axis, we would say it is even. Okay, that means on the y-axis, if you were to fold your graph in half, right on the y-axis, if it's a mirror image, if it's symmetrical, you'd call it even. So like the absolute value, the V-shaped graphs, that would be even. Now, here's the tricky part. That does not mean that all parabolas are even. For example, if you had a parabola like this, let's make it opening downward still. The graph is symmetrical, but it's not symmetrical about the y-axis. Do you see the difference? They're both symmetrical, but in order for it to be even, it has to be symmetrical on the y-axis. This is the y-axis, this is not. So it's symmetrical, but not on the y-axis. That would be a neither. It's symmetrical, but not on the y-axis. That would be a neither. All right, so that was just a little side note. So in order for it to be even, it has to be like a parabola or a V shape, but it has to have its vertex on the y-axis. If the vertex is anywhere other than the y-axis, it'll still be symmetrical, but not on the y-axis. Okay, odd. Odd functions, when you look at their graphs, are symmetrical, and again, you will need to know this for the test, symmetrical about the origin. All right, what does that mean? That means if you take your graph and you put like a little pin mark at your origin and you turn it 180 degrees, so just flip it right upside down like this, if you end up with the same graph, it is even. So I'm going to put it back and see if it's still the same. So this graph comes from the top quadrant 2 down to quadrant 4. So from quadrant 2 down to quadrant 4. Let me flip it again, 180 degrees rotation there and there. Does it still come up? This is now a new quadrant, 1, 2, 3, 4. Is it still going from 1 to 4? Yes, it is. It ends up being the exact same graph. So we call that symmetrical. So these cubic functions are symmetrical as long as, we'll call this the vertex, that little piece where it changes concavity, as long as that is at the origin. It has to be at the origin. For example, if I put it up here at, say, 2, you just have to pay attention to this one right now. If I say I shifted it up 2, and I can't rotate it at the 2, I have to rotate it at the origin, that is now negative 2. Yes, it's still coming up and then downward concavity, but it's happening at negative 2, not when it was originally at positive 2. So in order for these cubic functions to be symmetrical, we'll call this the vertex, that little piece there where it changes concavity, that little piece there would have to be at the origin. Okay, so what if, like I'll draw another one like I did over there, what if you did have one I just said was up 2, like that, what we're calling the vertex, that little piece where it changes, that 2 is positive 2. If I put my mark at the origin and I turn it 180 degrees, either way, it doesn't matter if it's clockwise or counterclockwise, and it ends up upside down, the graph looks the same, but now this point of this, where it intersects the y-axis, is now at a negative 2. It's not the same. That would be a neither. Okay, so even functions have to be symmetrical at the y-axis, which means that vertex has to be on the y-axis. The odd functions, and I don't think I ever wrote odd over here, the odd functions have to be symmetrical about the origin. So these cubic type functions, but this little point here has to be at the origin. And we will talk more about this in class. And that is it for this lesson.